Look around you. Almost every machine that moves our modern world, from the elevators and skyscrapers to the cooling fans in massive data centers, is powered by a silent, rugged workhorse. It has no permanent magnets, no brushes, and no electrical connection to its moving part. It's the three-phase induction motor. But how does a machine with no physical contact between its stationary and rotating parts create enough torque to move a Tesla or power a factory? The secret lies in a concept that feels like pure sorcery: the rotating magnetic field, or RMF. In this deep dive, we're going to strip away the complexity. We'll look at the math, the physics, and the sheer engineering brilliance that allows three stationary coils of wire to create a magnetic field that spins at thousands of RPMs. By the end of this video, you won't just know that it works. You'll understand why it's the backbone of the second industrial revolution. Let's get started. Before we talk about the spinning field, we need to understand the hardware. A three-phase induction motor consists of two main parts: the stator and the rotor. The stator is the outer stationary part. It's made of thin laminated steel sheets to reduce eddy current losses. Inside these laminations are slots where we wind three separate sets of copper coils. We call these Phase A, Phase B, and Phase C. Crucially, these three windings are physically offset from each other by 120 degrees around the circle. The rotor is the part that actually spins. The most common type is the squirrel cage rotor. Imagine a literal hamster wheel made of heavy conducting bars. Here is the catch: we do not connect the rotor to any power source. It is electrically isolated. So how does it move? To answer that, we have to look at the power supply. We aren't using standard DC power like a battery. We are using three-phase alternating current, AC. In a three-phase system, you have three separate voltages. They all look like sine waves, but they are out of phase by 120 degrees. When Phase A is at its maximum positive peak, Phase B and C are headed in different directions. This phase shift is the DNA of the rotating magnetic field. If all three phases peaked at the same time, the magnetic field would just pulse in and out. It wouldn't rotate. But because they peak one after another, the resultant magnetic tug moves in a circle. This is the heart of the video. Let's do some vector addition. When current flows through the Phase A winding, it creates a magnetic field. Since it's AC, the field grows, shrinks, reverses, and grows again. The same happens for B and C, just at different times. Let the maximum flux from one phase be phi m. The individual fluxes are phi A equals phi m sin omega t, and phi B equals phi m sin omega t minus 120 degrees, and phi C equals phi m sin omega t minus 240 degrees. First, the magnitude of the resultant flux is constant. It is always 1.5 times the maximum flux of a single phase. Second, the direction of this resultant flux rotates in space at a constant speed. Imagine holding a physical bar magnet and spinning it in a circle inside the motor. That is exactly what the three-phase current simulates, without any moving parts. This speed is called the synchronous speed. Synchronous speed, NS, equals 120 times F divided by P, where F is the frequency like 50 or 60 Hz, and P is the number of magnetic poles. Now we have a magnetic field spinning at, say, 3,000 RPM. Inside sits our squirrel cage rotor. According to Faraday's law of electromagnetic induction, if a conductor is cut by a changing magnetic field, an electromotive force is induced in it. This EMF creates a massive current flowing through the bars. And as we know from Lenz's law, the direction of this induced current will be such that it opposes the change that created it. To stop that relative motion, the rotor starts chasing the field. If the rotor ever actually caught the magnetic field and spun at the exact same speed, the magnetic field would no longer be cutting the bars. The induction would stop, and the torque would drop to zero. Therefore, an induction motor must always run slightly slower than the synchronous speed. This difference is called slip. That tiny lag is what keeps the motor turning. So, why do we use this instead of a DC motor? Self-starting. Unlike single-phase motors, three-phase motors create a rotating field naturally and start instantly under load. Robustness. No brushes mean no sparking and no wear and tear parts. Efficiency. They offer incredibly high power-to-weight ratios. To summarize, three-phase AC power creates three offset magnetic fields. The vector sum of these fields is a single field of constant strength that rotates. This rotating field induces current in the rotor. The rotor produces its own magnetic field and chases the stator field, creating torque. Engineering is often about finding the most elegant solution to a complex problem. The three-phase induction motor is exactly that, using the natural behavior of waves and geometry to create motion without contact. If you found this breakdown helpful, hit that like button. I'm also getting very close to a big milestone, 40 subscribers. Once we hit 40, I'll be doing a face reveal here on Simplifies. Do you have questions about synchronous speed or torque slip characteristics? Drop them in the comments below. Until next time, keep learning, keep simplifying. This is Simplifies, signing off.